Okay, hello and welcome. My name is Thomas Stroman. I work here at Google in search quality, and I want to introduce Frank Hutter. I've known Frank since my undergrad years in the Technical University of Darmstadt in 1998, and we worked together on a final project that involved writing an AI for the board game Mancala. And since then, Frank has worked on a variety of other applications in AI. So for his master's thesis in 2004, he worked on stochastic local search for solving the most probable explanation problem in Bayesian networks. And he also worked on using stochastic local search for the problem of RNA secondary structure prediction. And all these stochastic local search methods require a lot of manual tuning. So more recently, Frank has been looking into developing methods for automatically tuning parameters for algorithms. So for his PhD thesis in 2009 at the University of British Columbia in Vancouver, he did a thesis entitled Automated Configuration of Algorithms for Solving Hard Computational Problems. And this thesis won the Doctoral Dissertation Award for the best thesis in artificial intelligence at the Canadian University in 2009. Frank has also worked on a system called SATzilla, which does portfolio-based algorithm selection for SAT, and which won the 2010 Best Paper Prize for IHK/JAR. So today Frank will be talking about helping domain experts build better algorithms. Please welcome Frank to Google.
Thanks for the kind introduction. Right, this work is based on joint work with my postdoc advisors, Holger Hoos and Kevin Leighton Brown, and also with several others, in particular my colleague Lin Zhu, who is the main guy behind SATzilla. So I usually like to start this talk by pointing out some hard computational problems in both industry and society where building better algorithms actually really can make a difference. For example, in the optimization of industrial processes, or in the verification of formal properties of software or hardware and applications in security, or in the sustainable management of resources that our planet has to offer. But I figure here at Google, you really know that there's important problems out there and that building better algorithms is key to making progress on them. So let me jump straight to the central theme of this talk. So you're a domain expert in whichever domain that you work in, and there's problem instances you work with. You're trying to build better algorithms for solving those problem instances. Now, there might be a lot of algorithms out there already, and you're trying to figure out which one is the best to use for your particular instance set, or you're working on a particular algorithm of yourself, and you have some parameters of that algorithm that you can change, such as different heuristics or different optimizers you could use, or different numerical parameters, you name it. And all I'm going to require from these algorithms or parameter settings of an algorithm today is that you can actually run that algorithm on an instance and measure the empirical performance. And the talk is about automated procedures to model that performance and to optimize that performance. So notice that this is really domain independent. There is some work on meta learning. So if you have machine learning algorithms here and you learn about them, that's called meta learning. If you have optimization algorithms here and you optimize them, that's called meta optimization. But this is really a little bit more general than that. We can any type of algorithm down here. It could be a sorting algorithm or whatever, and you model their performance or optimize their performance. So I'm going to give 3 instantiations of these automated procedures. The first one is, well, just empirical performance modeling. So you fit a model that takes as input an algorithm or a parameter setting of an algorithm and an instance, and spits out something that's approximately the performance of that algorithm on that instance. The second one is algorithm configuration, where you have a potentially large space of parameter settings. In some applications, we have like 10 to the 47 different parameter settings, and we're trying to optimize in that space. So that's really a high-dimensional optimization problem. Try to find the best parameter setting for a particular distribution of instances, while, of course, avoiding overfitting and overtuning. And the third application is algorithm selection. That's a SATzilla work, where we try to find a mapping from instances to algorithms. So we're given a new instance, we extract some features, and say for this type of instance, that type of algorithm should work best. Okay, and again, all these methods are really domain independent, and it works on any kind of algorithms, problem instances, and also on any kind of performance measure. What you could be optimizing is runtime of the algorithm, or solution quality, or prediction error, or memory of your algorithm used, or even energy consumption in configurable data structures. It's very generic. Of course, in order to demonstrate that my methods work, I need to ground them in some applications. And today I'll talk about the propositional satisfiability problem, which is a core problem, of course, in computer science, and applications in software verification and hardware verification, and also about mixed integer programming, which is a very prominent NP-hard optimization problem that's used in industry a lot. And I'll talk about applications in industrial process optimization and computational sustainability. Now here's an outline of the talk. First, I'll give an approach for algorithm configuration, a fairly simple one that nevertheless does really well, and give two case studies, one for optimizing a SAT solver, one for optimizing a MIP solver, so that we kind of know the data that we're talking about. And then we'll talk about empirical performance modeling, about using those empirical performance models in order to do algorithm configuration better, in order to find good parameter settings using these models, and about using these empirical performance models for algorithm selection. All right, so you might be wondering what these algorithm parameters are that I'm talking about. So I have a very general notion of what constitutes a parameter. So it's really any type of decision that you make while you write your algorithm that is not hard-coded. That's an option. So it could be a real value threshold, or it could be a heuristic you use for a certain problem. You could use a different heuristic. You could use an optimizer or a different optimizer. If that's an option, that's a parameter. There's different types of parameters, of course. There's these continuous parameters, but there's also integer and ordinal parameters and categorical parameters. And these categorical parameters, those are the ones where you have a small, a finite, typically small subset, set of values that the parameter can take. Binary parameters are a special case of that, but you could also have, well, more values, such as use heuristic A, B, or C. The parameter space also has structure. For example, if you decide to use an optimizer, sub-optimizer A, then that optimizer has parameters of itself. And those parameters might have sub-parameters. So really the space spanned by these parameters is tree structured. And well, also there's a lot of parameters, so this really gives rise to a big space of algorithms where these configurations of the algorithm are different instantiations of all the possible parameters. And these configurations can often yield very qualitatively different behavior. Two different parameter configurations of one solver might be much more different than the default of that solver and the default of another solver. So that's why I like to think of this as actually different algorithms. And that's why we call it algorithm configuration, as opposed to, well, some people call it parameter tuning when you just optimize your continuous parameters. But that's a little bit of a different problem. Okay, here are some examples of algorithm parameters. I'm going to throw a lot up on the slide. I'm not going to talk about them. Here they are. So you can look at your favorite area. I don't know if it's combinatorial optimization or machine learning, etc., or search quality. There's parameters kind of all over the place. Typical parameters that occur very often are these pre-processing, like clean up your data. How do you clean up your data? How do you smooth it? Do you have, what type of data structures do you use? then which type of optimizers, and which parameters of these optimizers, etc., etc. So there's applications virtually everywhere. One type of application that's somewhat different, but very interesting in itself, I think, as well, are these subroutines in algebra or different data structures where you kind of think, well, that's a solved problem. How do you multiply two matrices or something? But different implementations do differently well on different platforms. And once you write an algorithm, you don't want to re-optimize the algorithm for every platform. But maybe you just want to push a button when you move to a new platform, or as part of the installation of a new system. You want the system to say, okay, which platform am I running on? Let's optimize for that. Okay. Oh, and I should say, if there's any questions where I lose you, please raise your hand, let me know. I'll try to answer it. If it gets out of hand, we'll defer it to later. Right. No questions at this point? Good. So we want to optimize over this parameter space. Here's a more formal definition of the problem. So you're given a runnable algorithm, its parameters, and the domains. And you're also given a distribution over problem instances and a performance metric. And you're trying to find the parameter setting, I'll call that configuration, of that algorithm that optimizes a metric over the distribution. Note that this is not just a black box optimization problem, but it's a noisy optimization problem, because we only we can run the algorithm. The algorithm itself might be randomized, so the performance metric of running the algorithm twice will be different with different random seeds, and we only get samples from this instance distribution. So if the algorithm does well on one instance, we don't necessarily know that it will do well on the other instance. And well, typically we need to gather a lot of samples in order to really be sure that the algorithm is doing well with a certain parameter configuration in order to avoid overtuning. The motivation for this problem is, of course, to, well, build these really general frameworks of algorithms, versatile algorithms that you can kind of take for, that you can use for different application domains, maybe different platforms, etc. So you have a very large space of configurations, and you have instance set A, you create a parameter setting for instance set A, and instance set B, you create a very different one that does well on that type of instances. And this is fully automated, as opposed to, well, the typical manual tuning that people often do, and you can optimize for any type of criteria. Maybe you get a very different parameter setting if you care about memory than if you care about speed or accuracy. Okay, so what type of methods would one use for algorithm configuration? Well, there's this discrete parameters, so discrete optimization methods would be a natural point to start. For example, stochastic local search, simulated annealing, etc., or population-based algorithms, genetic algorithms, evolutionary strategies, etc. But there's also this noise, so you could also use methods such as racing algorithms or bandits. So in practice, it's going to be some of both worlds. But there aren't really many approaches out there. Some people, few people, have studied this problem in, well, very narrow domains based on hill climbing and beam search in the early 1990s. But it has really been, there hasn't been any general method for general parameter optimization with many discrete parameters until 2007, when we first wrote an iterated local search for it. And since then, the field has been picking up, and there's more and more approaches coming out, and people are really realizing that it's much more convenient to push a button than to sit in front of your computer and optimize these parameters yourself. And we know that. We know humans are not good at high-dimensional optimization problems, at tuning these discrete parameters, many dozens of them, but people still do. So this is why people kind of like this approach, where you just push a button and it's done automatically. That's what it should be. Okay, so I'll talk about this ParamILS tool and about a second work of ours, the SMAC tool. First one is ParamILS, and I'll always, for each kind of sub-project, I'll have these overview slides and acknowledge all the co-authors on those. So this is a local search for algorithm configuration. And this is motivated by a simple manual approach for algorithm configuration. You start with some configuration, and you modify a single parameter at a time. If performance improves on your benchmark set, you keep that change, otherwise you revert back. And you repeat that until no more improvement is possible, or the solution is good enough, or you're out of time. And well, notice that this is really nothing but a manually executed local search in this parameter space. And what ParamILS does is to automate this and to put an iterated local search on top that avoids getting stuck in local minima. So the iterated local search runs into a local minimum by the same approach that we saw before, then does a perturbation to get somewhere else in the configuration space, and then does another local search to get into another local minimum, and then it decides which locally optimal parameter configuration to stick with for the next iteration. So it performs a biased random walk over a locally optimal solution, and if given enough time, it converges, well, it finds the global optimum, because a global optimum is also a local optimum. Now, what I haven't told you actually is how do you evaluate the performance of each configuration here? We have two instantiations of this framework. The first one is, well, really basic. You use the same fixed n instances to evaluate each configuration. And we have a simple variance reduction scheme where we use, well, also the same seeds, etc. The second instantiation is called FocusILS, and that only runs many instances for the good configurations. If you have a poor configuration, there is no need to run 1,000 instances on it. If it is really, really, really bad after a couple of instances, you know this is not going to go anywhere. I rather move on to some other configuration that might be much better. And also for FocusILS, we can prove a theorem that, well, as time goes to infinity, it converges to the optimal configuration. There's one more speed up trick I'd like to talk about. So if you minimize runtime, then you can terminate the runs for poor configurations even earlier. This is easiest to see in an example. So if the best configuration takes, say, 20 seconds to solve an instance, how long do we let this other configuration run? Well, definitely not more than 20 seconds, because we know at this point it's going to be worse than your best configuration seen so far. So no need to run it further. This would also work if you care for optimizing memory or energy consumption. And it provably doesn't change the trajectory of ParamILS, but in practice yields quite substantial speedups. Okay, that's all I have to say for ParamILS. I think the coolest thing about it is that it actually works. And there's a lot of different applications already out there, and many people from different groups around the world are asking us questions about it and how to use it for their domains. Today I can only talk about that many, so I'll talk about SAT and MIP. Those are two case studies I mentioned. So the first is a SAT solver for formal verification, and the second one is a commercial solver for MIP. Now SAT is the prototypical NP-hard problem, and therefore, of course, interesting from a theoretical perspective, but it's also important from a practical viewpoint. In particular, state-of-the-art methods for software and hardware verification are really under the hood based on SAT solvers typically these days. So we use two types of instance sets, one for software verification from my boy Garbage and Alan Hu, and a bounded model checking instance set from IBM. The SAT solver we worked with was called SPARE, state-of-the-art tree search solver, and it has 26 parameters. So 16 numerical ones, but then also 10 categorical ones, 3 of them Boolean, and 7 these heuristics, which can take up to very many values, up to 20 values. And these parameters give rise to over 10 to the 17 possible configurations. And that's what we're going to do optimization in, where running each configuration on an instance can, if it's a hard instance and a bad configuration, take hours. So it's a pretty daunting problem, and when we started this, we weren't quite sure whether this is going to work. But it actually did work in the end, particularly because when we find good configurations, then they're fast. So not all these runtimes are that slow. So what we did is just ran FocusILS for 2 days on 10 machines on a training set from each of the distributions. And that gave us one configuration for software verification and one for hardware verification. And we compared those to the manually engineered default by the algorithm designer. And he spent about a week performance tuning it manually. We compared on previously unseen test instances to avoid overtuning, of course. And here's a result for software verification. So the way to read this is a log-log scale. And if you're below the diagonal, the optimized setting is much better than the original default. In particular, there was no instance that it couldn't solve within 10 seconds, whereas the default sometimes ran out of memory or ran out of time after a day. So this is despite the fact that the algorithm designer here wrote the algorithm and generated those instances with his own Callisto static checker. So even though he had domain knowledge and knew his algorithm, he still, well, it's still a huge high-dimensional optimization problems, and humans are not good at that. Notice that for some of the easy instances, actually his tool, his default did quite well, actually better than the optimized setting. And that is because, well, in his tuning, he focused on the easy instances because, well, the hard instances take a long time. And that's what many people do. You use a fairly small set and fairly easy set in order to avoid these really long tuning intervals. But these automated methods actually have the patience to also look at harder instances and to look at many instances for the good configurations. Right, so overall, this was a 500-fold speed up on average. And based on that, Spare actually won a gold medal in the 2007 Satisfiability Modular Theories competition. For the hardware verification, the results weren't quite as impressive, but still very nice. 4.5-fold speed up with the same trend of better performance for harder instances. All right, so much for SAT. Let me move to MIP. So, yeah.
If you flipped the algorithm setting to the two problem sets, how did they do?
They didn't do all that well. The default was not all that bad. It wasn't actually great, I must say. Especially for the software verification set, it wasn't all that great. So using this set for here did quite okay. But we also did one study where we put the sets together and optimized on that. And, well, that did better than the default on the combination, but worse than the specially configured version, of course. So the more narrow your instance distribution is, the better performance you can get, of course, by optimizing on it. Yeah, this one here is a fixed configuration per distribution. So we optimized on like 300 instances for software verification, got this one configuration, ran it here on 300 other instances, and it did well. Yes? Sorry, what is the scale? This is seconds? So 0.01 seconds to a day. And
So do you think that if your exploration done is working, or just the fact that anything would work, basically anything would work here because the current things are so amazing and so bad?
I think mostly the latter one. I think we just need automated methods for doing this. I don't think my local search is any great. I mean, it's a state of the art, but it's still like, it's so simple, and there must be better methods out there. And I'm working on developing better ones. But it's a tough problem. But even a random search did actually pretty good. Random sampling in the configuration space did a lot better than the default if you automate it. So yeah, good question. But well, you need to worry about the noise, right? You can't just run random sampling and each configuration you run on 300 instances or so. That's maybe going to look at 3 configurations in 2 days, and it's not getting anywhere. So, yeah.
So the thing that you're optimizing there, is that just the average performance or runtime for instance, or are you trying to minimize the worst case?
Yeah, so here what we optimized is in fact the average across the instances. Well, actually the average very often works for the worst case because the worst case really dominates performance here. I mean, if you take the average of 100 runs where one takes a day and 99 takes 0 seconds, the day is still the important one, and you're optimizing for that. But if you really wanted to optimize for worst case performance, you could do that too. You would just use a different performance metric as an input. All right, let's move on. Good. Same kind of study for MIP. So MIP is mixed integer programming. It's very much like linear programming. This is a linear program, except you have some integer constraints on some other variables. So this combines the power of linear programming to deal with very many variables and the representative power of discrete variables. And that's why it's very heavily used in industry. What we worked with was the commercial MIP solver, CPLEX, which has been the leading solver for the last something like 15 years. And it's a real piece of software. It's used by like thousands of universities and corporations, including a third of the Global 500. And nevertheless, it has all these parameters. And the user manual says, oh, it's pretty sensitive to them. You might have to experiment with them to get good performance, despite the fact that they have all these customers. So there's over 50 categorical parameters. The space is even bigger, 10 to the 47 configurations. And we're going to optimize in that space. We use 6 different problem distributions, including industrial ones and some from computational sustainability. And first, we minimize the runtime to find the optimal solution. Got nice speedups factors, consistent, sometimes not very large, sometimes just a factor of 2 because, well, CPLEX is actually really well tuned, much better than SPED was in the beginning. But sometimes up to 50 for problem instances from this wildlife corridor application. Instances that must be somewhat different than what CPLEX had looked at before because it just didn't do very well and the scaling was, again, much better for our configuration. We also optimized the optimality gap that you could reach in a fixed runtime. So this is a gap between a lower bound and an upper bound, and once the lower bound hits the upper bound, you have proof that you have the optimal solution. So this is something you actually care about while you run. And yeah, we also got nice reduction factors for that optimality gap. There is a tuning tool that's built into CPLEX as of 2007 because they recognize that they have all these parameters and customers don't like that. But it's fairly simple. It just evaluates some good configurations and picks the best one for your particular instance set. And so typically you get a plot like this. You have the default, and after a given time, the tuning tool spits you out a configuration. So this is your budget over time, and this is performance, and you want to be lower. ParamILS is an anytime algorithm, and so over time it gets better and better, and it also beats the tuning tool. This is actually our worst result, and this is our best result for those wildlife corridor instances. And it turns out that the CPLEX tuning tool actually doesn't improve at all over its default there. So these must really be instances that are somewhat different than what they had looked at before. Okay. But nevertheless, this makes a point that in this space that they created with their parameters, there are configurations that can handle these instances well. And if you automatically search for them, you can find them. Good. Yeah, notice the log skill here, of course. Now, let me get back to the talk. So I talked about algorithm configuration and gave the case studies. Now, I'll talk about empirical performance models, and now we know the data, so we're done with the data. Empirical performance models, and then using empirical performance models for these 2 applications. Good. One question we often get from algorithm designers is, well, now you found this great configuration and it's doing really well. Why? What's important? Which components do I need to work on to improve? That we can actually answer with these empirical performance models. That's one example application. So here's a definition of the problem. You're given the configuration space and some feature space. So you have some features for each instance that characterize your instance somehow. And I'll assume that to be given. I'll talk a little bit about it. Next slide, I think. But mostly in this talk, I'll just assume it to be given. And you have some data, having run the algorithm with different configurations on some instances and collected the performance metrics. And you're trying to find some function that maps from the joint space of configurations and instance features to, well, something approximating the runtime or the performance metric in general. The motivation here is we want to explain the empirical algorithm performance, and we'll also want to use these in order to better optimize the algorithm and in order to pick the best configuration or best algorithm on a per instance basis. There's some previous work here. So these empirical performance models actually extend work from Kevin Layton Brown, Eugene Nudelman, and Yoav Shoham, which focused mostly on predictions in this instance space. So the type of instance features that they proposed were they had a long range of, a big range of features. I'm only giving a few here. Something like problem size. You can, for a SAT instance, you can look at different representations of the instance, different graph-based representations, variable graph, class graph, variable class graph. You can, importantly, run different algorithms. You could run a local search for a second and extract some statistics. How quickly does it hit a local minimum? How quickly does it improve? You can run a tree search. How many unit propagations does it do? How many clauses does it learn, etc. So you can, in machine learning, these are called landmarking algorithms. And so you can quickly gather some characteristics about the instance. And these are all polynomial time procedures that you run, and it's fully automated. Takes a few seconds typically if the instance is not too huge to get some knowledge about the instance. And the models that they used, well, they tried a bunch of different models, but what they ended up with is a fairly simple model, ridge regression, which is just linear regression with L2 regularization, but with some bells and whistles. So they had a quadratic feature expansion, and then they had all these features, and not all of them are important. So they really had to use some sort of feature selection technique. And for ridge regression, you can actually implement linear forward selection very, very efficiently with rank 1 updates. So that's what they used. And we compared that to different other models. So first, ridge regression, we put in a 1NK encoding to handle these categorical parameters and compared it to Gaussian processes. Gaussian processes, I had to put in a few bells and whistles. We have really large data sets, so like 100,000 data points or so. So Gaussian processes, which are cubic, kind of don't like that too much, so you need some sort of approximations. I used a projected process approximation. And I had to put in a different kernel for handling these continuous and discrete parameters. But it all works fine now. So it can scale to very large data sets. And then I also used regression trees, which are well known to handle discrete inputs well. And since they're a tree-based approach, they can also handle heterogeneous data well because they're directly hierarchical, right? And finally, random forests, which are just sets of regression trees, but typically have a much reduced variance. So since regression trees and random forests might not be all that familiar to you, I'll just give a quick example. So here's some data. We have we have parameter 1, feature 2, parameter 3, and the runtimes. So here's one run, another run, etc. And we want to build a model that maps from these parameters to that runtime. So what a regression tree does, it splits the data on a single parameter at a time. It selects that parameter by minimizing some loss greedily. So here we first split on parameter 3. The red data points go left, the blue and green data points go right. And all you store in this node is the split criterion you used. So that if the parameter was red, go left. That's all you store. And then you recurse into each of the children. Here we first split on feature 2. Then you only store the split criterion. Then you're in a leaf. In the leaf, all we do is store the mean of the runtimes. So 3.7 here. We don't have to recurse all the way. We can make this a leaf already, taking the mean of this, and recurse in the other subtree, etc. And we get a regression tree. Now you can use this regression tree in order to do prediction very easily. Let's do an example. Here's a new data point. We just propagate it down the tree. So first we look at parameter 3. Is it red? Oh, it's indeed red. We go left. Then we look at feature 2. It's 4.7. We go right. Prediction is 1.65. No magic. It's pretty simple. And actually computationally very efficient. And it also works well, as we'll see. Now random forests are just sets of these regression trees. They're simple to build. You just subsample the data t times. And for each subsample, you build a regression tree. And you build that regression tree in a somewhat randomized fashion. For prediction, you predict with each of the t trees, and you get the mean and variance across the trees. Done. Now, how do these methods actually compare in terms of predictive quality? So I'm going to show some runtime predictions for running CPLEX, the CPLEX default right now, on those wildlife corridor instances. On the x-axis here, there's a true runtime, and this is predicted runtime. So we want to be on the diagonal. If we're on the diagonal, everything is perfect. Below the diagonal, we underpredict the hardness. Above the diagonal, we overpredict. And this is rich regression. It's not doing all that badly. Actually, compared to all the other methods on this data set, it's doing just as well. And this is very much in line with what Kevin and his co-authors saw before. That's why they stuck with rich regression. However, what we found now is that once you go to more heterogeneous data sets, where you have a mix of different domains, then rich regression starts to kind of not do so well. So here's one example. Compared to, for example, random forests, it has these data points here where the easy instances, it just doesn't realize they're easy. This is 2 orders of magnitude here in terms of hardness. And it also has a couple of outliers. Actually, these here are, I only plotted them at 10,000, but 2 of them are predicted to be 10 to the 50 or something, a linear rich regression. It just is not very robust in that sense. Whereas random forests are a lot more robust and can deal with these heterogeneous data sets because they're hierarchically splitting the data. So next we'll look at the scaling with a number of training instances. Sometimes we don't have a lot of instances to train with. So here I'm plotting mini-SAT on some SAT competition data, and I'm plotting the correlation coefficient between the true runtime and predicted runtime. And we want the correlation coefficient to be as high as possible. 1 is perfect. And indeed, as we grow the number of training data points, we get better and better predictions. This is actually rich regression. And random forests are up there. Regression trees and projected processes are somewhere in between. And this is actually a picture that we see quite consistently across domains. Here's another picture for CPLEX on these heterogeneous data sets. And their rich regression really doesn't do anything until it gets a lot of data points, because the instances are so heterogeneous. Yeah, I said that. Now we want to do predictions in this joint space of instances and configurations. So I looked at data sets where we had 1,000 configurations that we sampled uniformly at random from this big configuration space. And we had 383 instances, and I ran every single configuration on every instance up to 300 seconds and gathered these 383,000 data points. And here's a plot of them. This is just the data, no learning yet. So there's these 383 instances here, ordered from easy to hard, and 1,000 configurations here, ordered from bad to good. And each plot each dot here is a runtime. So darker dots are easier. So the easy instances are solved by everything. Everything is black. The hard instances aren't solved by anyone. The good configurations, well, they're blacker here than the bad configurations. So that's the data. And as training data, first I used a subsample of 10,000 of these data points. So, and just had the approaches fill in the matrix. And here is a filled-in matrix with a random forest. It looks very much like the training data. So that's great, but we can't take that for granted. Not all methods actually do that well, even though it's on training configurations and training instances. It still needs to generalize to other combinations of them. Regression trees are just a little bit, have more variance. The GP starts to think some of the hard instances can actually be solved by the good configurations, and rich regression kind of doesn't really pick up on how important configurations are. It does pick up on the easy instances, etc. But random forests do best here. Now, how do they do for predicting on new instances and new configurations? So training data, just as before. And now the test data was, well, first, data on training configurations and training instances. We saw that plot already. Now we look at test configurations. So these are different configurations than these, but the plots still look very similar. So you can generalize to different configurations than you have trained with, and you can also generalize to different instances than you have trained with. And you can generalize to the joint, new instances and new configurations. Now, this is of course not always the case. Here is kind of our worst result for CPLEX on these wildlife corridor instances. We still pick up, well, at least that some instances are really easy and some are hard, and maybe a little bit of this trend, but certainly not that the good configurations can solve some of the really hard instances here. So it's not always perfect, of course. It's just a model, but the model is pretty useful typically. So let me get back to this domain here, because I have an example for that, for quantifying the importance of the parameters of SPARE on this data set. I'll have one slide of math. I'll go very quick. We'll rewrite the model predictions. This is a model prediction for its inputs, 1 to k, as a sum of components, as the average response across all the data points you've seen, plus the main effects. Those are effects due to changing one parameter only, plus interaction effects between parameters, plus higher order terms. And we can compute these components actually very efficiently. And then we can decompose the variance. We can say how much of the wiggling of your predictor is due to which component. So we can explain these, well, all this variation. Where does it come from? Does it come from parameter 1 or parameter 2, or from the interaction of parameter 1, parameter 2, etc.? So you go about this by just writing down the variance. The variance by definition is the predictor minus the predicted mean squared, and integrated over all the inputs. And then you do some math, and out comes some terms for each particular effect. So here's the effect of parameter 1 integrated over just parameter 1 squared, plus the effect of parameter 2 squared, etc., plus the interaction effect, plus higher order terms. And so we can say how much of the variance is due to each of the parameters. And importantly, for this SPARE algorithm on IBM, 93% of this variance was actually due to one single parameter, which in this case was the variable selection heuristic. And people know that the variable selection heuristic in SAT solvers is really important. So what we can do is plot the average predicted runtime for each of these options. And we can only plot this, well, this really is, it's an exponential sum. It's the average runtime. It's averaged over all possible values all other parameters could take. So it's an average over 10 to the 17 terms, but we can compute that in linear time in regression trees, actually. It's really nice by just doing some operations on the leaves and filling in that data. But let's get back to this actual example. So these heuristics here, these options 0 to 7, they were activity-based heuristics, which look at how often is a variable used and how often does it occur in learned clauses, etc. And all of these heuristics are pretty good. They give you average runtimes, except this one heuristic, well, that actually was pick the least active variable. So really these activity heuristics are good here, and that's useful information for the algorithm designer. There's some occurrence heuristics here that are just static heuristics about how often does a variable occur in the formula, and then some other heuristics that are miscellaneous. Now let's compare this plot to the same plot on another data set. You have a very different picture for the software verification set, these activity-based heuristics. Well, some of them still do well, others don't do very well anymore. And in particular, you have this one parameter setting here, that one heuristic that does well for software verification, but does not well for hardware verification. This was a heuristic that just took the variables in the order they were created. Variable 1, 2, 3, etc. And that's a really trivial heuristic. How could that work? Well, it can work for some encodings because the order of instances actually has meaning. And nevertheless, the domain expert we talked to had really no idea which heuristic is going to work well here. He was like, well, one goes top down versus the encoding graph, the other goes bottom up. I don't know which one would do well. The other one, the reverse one, was actually heuristic 17, which did the worst. And he didn't know beforehand, right? So after gathering this data, we can learn a model. Learning the regression, the random forest on 10,000 data points maybe takes a minute or so. And then we can generate these plots in about a second and tell the domain expert, here, this is 93% of the variance explained. That's where it comes from, and this heuristic here is the best. And that's really useful information for domain experts. This is really new work, but I really hope this is going to change a bit the way that people deal with the algorithms, that they do more experiments over time and just look at plots like these, explaining them, where does my performance come from. All right, I should hurry up, but actually these are only going to take like 5 to 10 minutes. So I'm going to use empirical performance models for algorithm configuration. I already talked about algorithm configuration. That is, find the best parameter setting for a set of instances. And now we're going to use models for doing that. This work is motivated by Bayesian optimization methods, in particular efficient global optimization, the EGO algorithm by Sean Welch, which works as follows. So it's for optimizing some black box function. Here's a function. I can only plot a 1D function. So here's a parameter x. We want to minimize this response over parameter x using these models now. So EGO starts by sampling, by taking an initial design, typically a Latin hypercube design, and getting the performance values of that black box function. And it's a black box function, so really this is all you see. You have some values, and you're trying to optimize this. So what you do is fit a model. Here, fit a random forest model. And then you compute a so-called expected improvement criterion that tells you which configurations are predicted to be good. So they're predicted to be good, or you're unsure about them. So you have an automatic trade-off between exploration and exploitation. Exploration of new unseen regions of your configuration space and exploitation of low predicted runtimes, for example. So you optimize this empirical, this expected improvement criterion over the parameter space, and at its optimum, you pick a new point and you run the algorithm with that parameter setting. You get a new point, and you've done a lot of work just to get one new data point, and you just keep on doing that. Now you build a model again. Here where you got the new data point, the model changed a lot. Now you're going to pick this next, and so on. And you iterate. In adapting that to algorithm configuration, there's quite a few challenges. One challenge is, well, typically these Bayesian optimization methods work for very few numerical parameters, less than 10. And they only do maybe 100 function evaluations or so. For us, for algorithm configuration, we have up to 76 parameters, and they're discrete and continuous, and we do 10,000s of runs maybe. And so the models really need to scale. And the computational overhead for us is actually part of our budget. So if we have 2 days to optimize the algorithm, we don't want like 1.5 days of that spent to learn the model. So we really need to be cautious about learning quickly and using and optimizing this expected improvement function quickly. The noise is highly non-Gaussian. It's completely normal for a local search solver, for SAT, and also for tree search solver. You run it once, it takes a second. You run it again, so it takes 10 seconds. You run it again, it takes 0.1 seconds. That's the kind of noise we're dealing with. And there is a lot of noise coming from instances as well. So we need to use these instance features in order to marginalize across instance space. There's conditional parameters, so there's parameter structure. And if we cut off algorithm runs early, then we only have a lower bound on their runtime. So we really need to work around that, and there's not really a lot of approaches, for example, for GPs. But yeah, we have an approach for doing that with random forest, but I don't have the time, of course, to go into detail there. But I'll be very happy to talk about any of these challenges offline. In the end, we have this algorithm, SMAC. It starts very much like Ego. It performs some initial runs and learns a random forest model to predict the algorithm performance. It uses that model to pick a set of configurations now, not just a single one, and compares each of them to the so far best configuration, using a similar heuristic as in focused-ILS and doing many runs for the good configurations. You repeat that until your time is up and return the best known configuration. We can prove the same theorem as for focused-ILS, that if we have enough time, this converges to the optimal configuration. We compared this experimentally to ParamILS and GTA, the other two methods out there, gave them the same time budget, and SMAC performed best, only by a small margin, but still up to twofold or so, because ParamILS already found really good configurations. But this can also find the same configurations faster. And this is still under active development, and we're pushing it further and further to reduce the overheads of algorithm configuration. We don't want to wait 2 days if we could do it overnight, for example. All right, there's algorithm configuration. Finally, algorithm selection. We want to select, for a new given instance, the best algorithm. That's basically the definition. And the motivation behind that is we want to take that instance, run it, extract the features quickly, then run our algorithm selector and pick, well, the best algorithm for it. Why do we want to do that? Well, a lot of algorithms have different strengths and weaknesses. Some algorithms work well on structured instances, others well on random instances, etc. And we want to exploit that. And SATzilla is one way of doing that. So what SATzilla does during training, it just builds an empirical performance model for each component. And then at test time, it predicts the runtime of each of the algorithms and picks the best one. Simple enough. This core approach actually was introduced by a group at Stanford when Kevin was still there, prominently featuring Eugene Nudelman, who is also at Google actually, and their supervisor, Yoav Schwam. And when Kevin moved to UBC, we continued that work. What we did is to put all kinds of bells and whistles around to make it more robust. For example, we put in pre-solvers. Feature computation might take a lot of time for very large instances, and we just run one solver very quickly to already get a bunch of the easy instances out of the way where we don't need to run feature computation. Some solvers crash, and you still have time left. You might want to run some backup solvers in that case. And we have a fully automated approach where you just stick in algorithms and instances, and out comes a portfolio of solvers. Also, having too many component solvers can hurt you if your model is actually not too great for them. And by dropping some algorithms for which your predictions are bad, you might actually improve the performance of your portfolio. So we have an automated procedure for that. And most recently, we put in a new classification method based on random forest that also exploits these hierarchical, that is good on hierarchical. It's a hierarchical model, good on heterogeneous data sets. Sorry. SATzilla did really well in the SAT competitions. Already the core SATzilla did quite well. And in 2007 and 2009, we won like 10 medals together. And in 2009, for the first time, that actually included one gold medal in each of the categories, so in industrial, in handmade, and in the random category. And nobody had done that before. Of course, this just utilizes the strengths of our component solvers, which were in turn good solvers for those types of instance sets. In 2011, we only submitted it to the evaluation track in order not to steal all the medals from the real SAT algorithm developers. Actually, there were a bunch of other people putting portfolios in, so half of the medals still went to portfolio solvers. But SATzilla would have won all gold in all of the categories using the portfolio solvers from 2011. And it closed like 80% of the gap between the best solver and an oracle picking the best solver for each of the domains. For random, 55% and 33% for the other categories. Finally, you can combine this with algorithm configuration. If you only have one strong solver, you can run your feature extractor, then select the parameters to use for that instance. That is non-trivial because the space of parameter configurations is exponentially large. But what we do is to run algorithm configuration to find some complementary configurations and then selection using those configurations. And this always improves performance at least somewhat, and sometimes very much, depending on how heterogeneous your data set is. Okay, let me wrap up. I talked about automated methods for modeling and optimizing algorithm performance. 3 methods: empirical performance models fit this model, algorithm configuration found the best configuration for a particular problem set, and algorithm selection picked the best solver for each instance individually. We can use these performance models in order to quantify and visualize the importance of each parameter. For algorithm configuration, I showed 2 methods, ParamILS and SMAC, and 2 case studies for SAT and MIP where we got orders of magnitude improvements. And in algorithm selection, we looked at SATzilla and Hydra, which did really well in the SAT competitions and can combine algorithm selection and configuration. In future work, I have a lot of ideas for algorithm configuration. You can do algorithm configuration on the cloud. Parallel algorithms have a lot more algorithms than non-parallel algorithms. And you can also exploit the massive parallelism in order to do algorithm configuration faster. Finally, I like to collaborate more with domain experts, and we've started a variety of projects and to improve the state of the art in various areas. More generally, I think really more and more complex systems will have more and more automated methods for optimizing their parameters because computer time is getting ever cheaper and human expert time is not. So I really think that automated configuration and automated methods in general will be a growing field. And I'd be thrilled if there's any applications at Google for sure. So with that, thank you for your attention, and thanks to my co-authors. Any questions? Yeah.
Two-stage process that you do. You're not trying to vast amount of data.
Mm-hmm.
Parameters, and then you exploit them to stage.
Yeah.
So it's very cheap, relatively cheap to fly out changing the later parameters, but expensive to fly out changing the earlier parameters. Have you done anything where you account for the different costs of exploiting different parameters?
Yeah, so the question is on two types of parameters, one top-level type of parameter and then sub-parameters. Is that the question? Or?
Not exactly. So
okay.
Suppose you're doing machine translation.
Yeah.
Okay. So you have some parameters that will happen at the end to.
Oh, okay. Yeah.
You also have parameters that control learning from your vast corpus.
Right.
And changing one of those, you just over your entire corpus.
I see. Yeah. Very good question. So the question is, you have parameters that act in certain stages of while your algorithm is running. It's not just your algorithm runs, it's a black box, but really it's not a black box, it's a gray box. You can kind of have checks over the course of the algorithm, and some parameters only come in later. We haven't looked at that. My intuition is that, yeah, of course, it would be a lot cheaper to optimize the later parameters because you don't need to do as much work. And smart methods would exploit that and would exploit all the work you've done up to there and not redo that work once you evaluate a new configuration that only changed one of those parameters. Yeah, interesting problem. Yeah. Right, so the comment is all algorithms are kind of like that, and you have control over the algorithm if you can control the compiler. I haven't thought into that level of detail of yeah, really changing your compiler options. I mean, there's actually work out there in optimizing compiler options as well. But yeah. Yeah, I think that would be an interesting challenge for algorithm configuration, and with potentially massive gains, because you would save redoing a whole lot of work. But I would have to think more about it. Yeah. Mm-hmm. Right, so the question is, have you looked at the log online to maybe online change your parameters? And well, what we have done is a bit of that. We have looked at the log to actually generate features. We run CPLEX for a short amount of time and extract features from the log. But so far, it hasn't been an online process. We get some features once in the beginning, and we use that. But there is work out there in controlling your algorithm parameters while you run, but it's a lot more tricky because now you don't have a clean learning problem anymore, a clean supervised learning problem. You have a reinforcement learning problem, really, because you change your actions, and really, if you solve an instance in the end, it's now you have to attribute that success to the changes you've made. And so really, you don't have this configuration did this well, but it's this configuration first, then that configuration, then that, that solved the instance in this time. So that's harder. Right. Mm-hmm.
And then you can say, from what I've done before, I know that I only need that 10 minutes to solve the problem. And you don't change your graph, just plug 10 minutes.
Mm-hmm. Yeah, that that is interesting, and that in fact does seem like a clean learning problem where you just you collect the data while you run and then just predict how long will you run from here. You'll have to have features that are time invariant, right? Or you have to have different models at different time intervals. You probably don't want to do that. You probably want to have time invariant features, and then it's really about how much progress am I currently making. There have been some approaches for trying to figure out how much progress is being made, like satometer for SAT. But yeah, I haven't seen any breakthroughs. And for local search, it gets even harder to really make sure how much progress you're making. Yeah.
You had some close examples that are very hard problems that often don't even stop. So this approach was suitable for that, or did you try polynomial problems as well?
That's a good question. Have we tried polynomial problems? Not so far, really. I mean, we're starting to look at them. We had one student looking at sorting, but you know that was more. She was an undergrad, and it was a summer project. But I think very similar methods should work for polynomial time problems. And actually, some other people have done some work on polynomial time problems, more in terms of selecting the best parameters on a per instance basis. But you know, all these configurable data structures or something, that's all polynomial time, and I'm just not a domain expert in it, and I haven't really had a lot of interaction with domain experts for those polynomial time problems that also have a lot of parameters. I know a lot of theoreticians, but they're like, yeah, I have one parameter. And maybe, actually, one of them is getting really excited about this work because configurable data structures are getting hotter and hotter. Because, for example, for energy consumption on your Android phone, you might want to have very different data structures than on your compute server. And you don't want to go tune them everywhere. You want to have an automatic method. And they're starting to put more parameters in, but they don't have all that many at this point. All right, thank you.